I'm Darren LaPierre. I'm one of the studio engineers here at AudioLink. Today, we'll be talking about lossless digital audio, specifically sample rate and bit depth. Let's get started. Analog audio is an electrical signal where the voltage of the audio signal varies continuously with the pressure level of sound waves. Bit of a word salad, isn't it? All you really need to understand is that analog audio is a pure electrical signal that can be transduced from or into sound waves. For example, here is a simple sine wave. An analog signal can replicate this perfectly. First, we'll draw the y-axis for voltage and then the x-axis for time. I'll draw a sine wave with its peak and its trough. Just like that. Yep, looks right. That's a sine wave. So how would a sine wave be represented in the form of digital audio? Digital audio is an analog audio signal that has been converted into bits of digital data. The continuous variations of voltage are quantized into discrete values of voltage and time. This digital audio can then be reconverted back into an analog signal for playback, and your ears won't notice any difference if you are using a high enough sample rate and bit depth. Let's look more closely at this digital representation of a sine wave. You'll notice that the red sine wave on the graph is now gone, and those little purple lines to show the discrete values over time are on their own. These lines along the x-axis of the graph represent the samples, which are snapshots of the waveform over time. The line's heights along the y-axis are determined by the amount of possible bits the sample can achieve, which is determined by the bit depth. Let's break down these concepts a bit more. Sample rate is like the audio equivalent of video frame rate, where every second there is a certain amount of images that are displayed on a screen. This controls the motion and smoothness of the video. Now, the frequencies of sample rates are typically way higher than video frame rates. In order for it to sound pleasing to the human ear, sample rates are usually at least double the frequency threshold of human hearing, 20 kHz, to avoid unwanted noise and artifacts generated by aliasing. What's aliasing, you ask? Well, aliasing occurs when frequencies above half the sample rate, known as the Nyquist frequency, are improperly sampled due to insufficient data being present for each cycle of the waveform. This generates inharmonic frequencies and noise that are not part of the original analog signal. Fortunately, this effect can be easily negated with the use of high sample rates. For example, the sample rate used on commercial CDs is 44.1 kHz, which means that aliasing will occur beyond 22.05 kHz, which is well beyond the frequency range of human hearing. 44.1 kHz is the least high-quality sample rate used in audio. It is the standard for CDs and most streamed audio. Video, however, is slightly higher. 48 kHz is the industry standard. Why? Well, 48 kHz not only raises the threshold of aliasing with an increased Nyquist frequency, but it is also optimal for video sync, as 48 kHz is mathematically equivalent to all standard video frame rates, such as 24, 30, and 60 frames per second. Now, there are even higher sample rates such as 88.2, 96, and even 192 kHz. These are used for their high Nyquist limits, and because they encode more waveform data per second. This is great for post-production and large-scale audio and video projects to avoid data loss over time. However, in most practical cases, using 44.1 or 48 kHz is good enough. Now, let's switch our focus to bit depth. Bit depth is like the audio equivalent of video resolution. The more pixels there are per frame in a video, the higher the quality of the video will be. Now, if we look back at that graph I showed earlier, each sample point on the digitized waveform holds a specific value that is determined by the number of possible bits. Bits are binary numbers, which means they can only either be a 0 or a 1. Let's show the possible amount of voltage points a few bit depth values can record. First, I'll start with 1 bit. This leaves us with two possible values, 0 or 1. Now, with 2-bit, we have a sequence of, well, 2 bits. So we get 0, 0, 0, 1, 10 or 11, 4 possible values. Now, with 3-bit, that's a sequence of, well, 3 bits. And, well, I'm not reading all that. But you can see where I'm going with this. In total, there are 8 different values. The greater the value of the bit depth, the higher the amount of voltage data that can be recorded. Any bit depth below 8-bit does not have enough data points to properly reconstruct the audio waveform without noise and artifacts. The lowest acceptable quality bit depth for most digital audio is 16-bit, the standard for CDs, DVDs, and streamed audio and video. The larger the bit depth, the greater the dynamic range of an audio file. Because of this, engineers will often use a bit depth of 24-bit or higher to achieve an even larger dynamic range. So, with all that info, you may be thinking to yourself, the higher the sample rate and bit depth, the better the quality, right? Well, the other aspect you have to consider is file size. The values of sample rate, bit depth, time, and the number of output channels of the audio file will all directly affect its size. For example, a 3-minute stereo audio file recorded at 44.1 kHz, 16-bit, will take up 32 megabytes of space, whereas an audio file recorded at 192 kHz at 24-bit with the same parameters will take up 207 megabytes, which is 6.5 times larger. If you're curious about how these calculations were made, here is a list of equations and examples that led to these values. It is extremely important to be wary of file sizes when using high sample rates and bit depths for the sake of digital storage. Keep in mind, lower sample rates and bit depths below 44.1 kHz 16-bit, such as 8 kHz 8-bit, are sometimes utilized for files to take up even less space. However, the audio quality will definitely suffer, and there are better ways to do this, such as using MP3s. Low sample rates and bit depths can also be used for sound design, as digital audio at these levels is quite noisy and distorted. This is often achieved with the use of effects that emulate low sample rates and bit depths. So, what did we learn today? Let's take a look at this chart. On this chart, information about a few different sample rate bit depth specifications is provided. Let's discuss which parameters are right for your project. The standard option would be 44.1 kHz 16-bit. This will provide the smallest file size among high-fidelity options and will ensure playback across most devices. If you're working with film or video, stepping up to 48 kHz 24-bit is a better option while increasing file size. The sample rate of 48 kHz will sync with the standard 24 frames per second frame rate. If you'd like to provide higher fidelity, our next jump is to 88.2 kHz 32-bit. This will double the fidelity of the 44.1 standard, while still providing a smaller file size than extreme options. 96 kHz or greater will make for massive file sizes. However, if you'd like your digital audio to be as close a representation to its analog source, sample rates of 192 kHz could be an option. Just be aware that you will experience diminishing returns in fidelity with every step up in sample rate. Well, that's it for today. Next time, we will discuss all the different types of audio file formats. See you next time.